Yeah, that's because there's an accented eye that looks like that, I think, with the upward V. So I'm like, wait, am I adding a bunch of random accents? Yeah. Different variations.
I have a question. I got particularly stuck on these two questions. What wave particle duality means, and what it means for light, and what it means for electrons.
So what do you know about light and maybe some of the weird things about it, or
I mean,
how is it a wave? How is it a particle?
I know that basically we see light is it's hard to explain. I guess it's basically electrons, I guess, diffracting off of atoms, right? And we perceive it as light.
Well, right, when the electron relaxes back down, it releases energy,
Right.
so then we see that light.
Right.
So it's
Yeah.
different, but then, so do you know how light is like a wave?
I mean, the wave is our, I guess, our way of measuring the energy, right?
And then, so that would also correspond to like all the frequencies of light that we
Right.
see, and
Right.
the fact that it moves at, 3 times 10 to the 8th meters
Yeah.
per second. So all that is wave behavior. It also does the diffraction patterns. But then what about the particle part of light? So think back to like Einstein shining the light, right? And so what was the problem with the light? Because you had like the red light versus the blue light. And what did that tell us?
I know it has something to do with this, I forget what the instrument is. It like divides the light so we can see it correctly.
Yeah,
It has
so
something to
there's
do with that.
that aspect, but we have to think about what's going on. So the problem was, if we think back to Einstein, right? So he was shining the red light, and nothing was happening, right? So it wasn't ejecting an electron. And so part of that is like each little packet of light, and so we didn't know that, right? It's like each light is like a packet, right? So it wasn't the correct energy, so it didn't match any frequency. And then he changed the light to blue, so now blue, right, higher energy. And now that was the appropriate energy, right? So now each little packet of light hits it, that's the correct energy to promote the electron. But it was the whole, the thing that came with that was that it was a package, right? So it didn't matter how much we shine the red light at it, it didn't do anything.
It just give the reaction that we wanted.
Yeah. But then that was telling us, oh, well, there are these things of photons, of like individual little lights that we see. So they're really like little packets of light energy going as a wave. And then, yeah, electrons,
So I just want to be able to sum it up so I can, I guess, write it down. The wave particle duality is we have the full just light in general. It's like portions of each. I can't put it in words.
yeah, so you can say, right, it moves like a wave, so it moves like at the correct speed, but then it's also quantized, so it has little photon packets, so that means it's like a particle. So it's like a little photon particle almost.
Okay.
And then electrons, so right, they exhibit some wave behavior because they're moving so fast. So they're not moving at the speed of light, right? But we mentioned their de Broglie wavelength is relevant.
Right.
And then we mentioned also the diffraction pattern that electrons create, so that's wave pattern.
Okay.
And then of course particle, it is a subatomic particle, it has mass.
Okay. I think I got it. All right.
Yeah, it's hard, weird stuff. Okay, I'm gonna be back. All right, before we dive into our ionic bond formation, I just lost, there it is. I just wanted to at least briefly talk about the exam. So I have not finished grading officially. I'm almost there. So I just have the back page of everybody and then to tally it. But it's not looking so well. So I don't have the grades, but some people did not do very well, and it was not good. So that being said, I will offer exam corrections. Yeah, so everyone will be able to do exam corrections. So when I finally get those back to you, you'll be able to correct your exam for 70% back credit. And so you'll see your exams when you get it, but I didn't want anyone to be like super unhappy over the weekend if those grades go in. And if you really want your grade, you can maybe hound me and I can finish your exam really quickly. So I'm going to be trying to do that while you both quiz and then hopefully in lab, because I want to get that back to you. But I'm just putting that out as a heads up so there's no super unhappy people, and know that there are opportunities to regain credit back. And yeah, a lot of little like algebra errors too, so you'll see that, but we can say that for next week unless there's like a burning question people want to go over. All right, we can come back to the exam if people want to talk about it later. But since there is silence, we'll go back to this. So quick recap, where were we? So we were mentioning, well, what really drives that ionic bond formation? And so, right, we were breaking down this process. So we said we had sodium plus chlorine, and of course they make sodium chloride. And then we had broken them down to the individual process. So we know, right, sodium has to give up an electron. So that's formally the ionization energy. And then we noted, so this is endothermic. And right, we can also calculate this for an individual atom if we needed to from this data, since it's per mole. And do people know Avogadro's number? So we could do that conversion. 6.022 times 10 to the 23rd. And so that's individual either molecules or atoms in 1 mole. So this is just a relationship. But then if we wanted to, so now that I've mentioned it, I guess we'll do it. So now we can say for 1 sodium atom, and so this is in kilojoules. I'm going to put into joules before I get lost on my units. So 496. So now I have 496,000 joules, and then I want to know 1 molecule, what that energy is, so divided by our Avogadro's number. And so then we get 8.23 times 10 to the negative 19 joules. So that's one way to also get those calculations, but I think your book also has it in maybe attijoules. And it's right, so that would be 0.823 attijoules if you like the attijoule unit. And so then same thing, so then we said, right, the chlorine process. And so, right, we have half an equivalent of our chlorine, so diatomic, is then adding an electron. So we mentioned that electron affinity process in the gas state. And so we mentioned, at least for chlorine, since it's on our right side of the periodic table, oops, I don't have a periodic table. So of course it's on the right side of the periodic table, some more electronegative, right? It almost has a full octet. So that had a exothermic electron affinity. Again, we could calculate the individual one as well, just dividing. And so then we were left with this question. So we said, so the heat of formation of most ionic compounds is exothermic and generally large. So why was that? And of course, we could add these two values together. And you could probably see that it gives you a positive number, but let's just add it. So plus our negative 349. And so this is showing us with just looking at these two factors, right? It should be endothermic, so it should require energy. But that's not true. And so the extra energy we mentioned was in the crystal lattice structure. So this is, again, extremely important. And so this is the lattice energy that accompanies the formation of the crystal. And so it's always going to be exothermic. And of course, it would depend on the charges and inversely on the distance between ions. And so then we're given this Coulombic energy attraction. And so we can just plug in our Q. So this is, right, charge 1 times charge number 2. And of course, right, you can see what they were saying. So they said that it depends on the size of the charges. So of course, larger charges, greater attraction, and inversely on the distance. So of course, greater distance, less attractive forces. And so with the calculations, you usually find the discrepancy, of course, in this little d. And so that just depends how you get the value. So sometimes you could look it up if you wanted to scour the internet, right? You look at, like, let's look at sodium chloride. Let's even see if it has this information. So sometimes you can find a bond length.
What does D represent?
D is the distance. So it's the distance between them. Now let's ask the internet now. So sodium chloride distance. And so according to this, so this is drawn from crystal structure data. So it's saying, right, in their crystal structure, the distance is 2.814 times 10 to the negative 8 centimeters. So that's one way to get it. And so I'll just say, like, from the internet. And so 2.814. And so how else could we measure it? So let's just say from our textbook now, and we'll kind of see how they compare. And so the distance you can also get just by adding the two radius together, right? Because you'll have your sodium cation, smaller radius, and then our chloride, large radius. And right, if we add those two radiuses, that will also give us the distance. But again, numbers may vary. So let's see if I can find those notes. Trying to find our distance and cation, anion size. There they are. And so we can look here. So our sodium cation is 95, and so this is picometers. And where's our chloride here? Oh, we have to look at anions. That would help us. So 181. So let's add those two. So 95 plus 181. And so this is in picometers. And actually, it looks like this one will be pretty close, but. And so from textbook, from adding them, so 279 picometers. And so those are pretty similar values. But again, there could be small discrepancies in your distance. So just know that with your numbers. And then so looking at this formula, though, it wants you to have your distance in picometers. So just watch that. So we could either convert centimeters to picometers, or we can just stick with our textbook value here, which is going to be what I recommend. But again, I'm just saying you could find other values and other discrepancies, or if you use a different chart with different radius numbers slightly, that's where probably it's going to come from. So just be aware.
Why is it not like a set radius for all of them?
Well, because it's going to be how they exactly pack, right? So when like two different atoms interact, right, their bond distance will change slightly, and it also depends like on the entire surroundings, right? So like even just in chemistry, like every carbon-carbon bond is not the same length. They'll all be pretty similar, right, because they're all like, especially if you're looking at single bonds, but they all just vary just slightly with those little electronic, interactions and everything around it to the entire molecule. And so yeah, you could get into everything as well, and so that's always part of the debate, because when you look at the solid state structure, right, it may not be representative of how it's behaving, in another state. And obviously, if we're looking at a crystal, that's kind of more representative, but like if you crystallize a molecule and you look at the bond distances, that's just in the solid state. You're not quite sure if that holds true in the liquid state and the gas state. But. All right, so let's plug it in with this value to practice. So now our energy, and if we're doing sodium chloride, so it's just 1. So our 1 charge times our -1 charge over our distance. So if we can keep it in 276, because again our picometers will cancel. And then times 231, and then we're in attajoules. So we're going to get out attajoules. And so now 231 divided by 276. And so that gives us 0.836 or 0.837, I'll round it to, for our Coulombic attraction. And then that is negative, so don't forget your negative sign, which we were expecting, so negative being exothermic. Questions? Yeah, so it's the charge of each one, and then the Coulombic attraction is, like how much that force is pulling them together then.
Do we then turn this number and figure out like how much force it would take to break this?
Yeah, so then this would be the force required to break that. So you could think about it, right, with your dissolving now interaction. So that's part of like, will it dissolve or not? So how much is this Coulombic force? And then the water has to come in and also overcome that interaction. Exactly.
So we could do like water and see if it's greater than this number here?
Well, we don't have a good formula, right, to calculate the Coulombic attraction between our oxygen and our sodium. So it's not like as neat, but that's kind of the idea, is like, is that solvation, more than this?
Also, if it's more, it's dissolvable?
Essentially, yeah. But that's just more like theory, because that would be like harder to quantify, but that's where they get kind of, the solubility trends. And then when we talk about solubility later, that might explain some anomalies, that just their Coulombic attraction is too strong and the water just can't overcome that.
So is this attajoules thing that you're multiplying everything by, is that a constant, or does that change depending on the molecule?
No, it's a constant, so it'll always be this formula. So the only thing that's ever changing is, of course, just your charges on the molecule and then the distance you have to plug in. All right, I'm going to flip to chapter 7 notes, but we can I put another, it was supposed to be a warm-up, but we didn't quite finish. So let's see if you can calculate this then. I might need to rewrite the formula. So energy Coulomb was 231 attajoules, and then times our charge, so Q1, Q2, over D. And if people need distances, let me know. So while you punch that out, I'm going to hand out a polyatomic sheet. So this will help you for ionic compounds. And if polyatomics crop up in your life, you'll be ready.
Do we know the radius of the lithium and fluorine ions?
So if you don't have your book, let's look at, so lithium's radius is 60. And then which other one do we need? Fluorine, you said? And fluorine is 136. So flip back over and hold these values on my calculator. So let's hear some values. What do we get when we punch this in?
Negative 1.18.
Negative 1.18 attijoules. And then, is that what other people got? So I see some. So yeah, 1.19. Yeah, that's a little discrepancies expected, but that sounds good there. All right, so now what do we need to do with this one? What is it asking? So then how do we figure out our energy release? What do we need to all put together? Excellent. So we have to put all the processes back together. So ionization energy, or sorry, electron affinity of fluorine, like you were saying. And so just breaking down that process. So adding our electron, and then you said our ionization energy of lithium. Again, that process of removing an electron, oops, plus ionization energy. And so for these, I think the book has a chart, right? I'm pulling. The book is being slow. And so on an exam, I would have to give you some chart, or I guess I do give open notes, so you could reference your chart. So let's try to find it in our book. Does anyone have the book page by any chance where it's? Trying to find, where's everything?
I know the ionization energy chart is in chapter 4, but I don't have the page.
Okay, I'm at least in chapter 4. Oh, nice. So we have fluorine, and so we have our ionization energy. And so right, this chart, you may want to sticky note it or note it down somewhere for when you do these problems. So you have some ionization energies on 107. And so thank you all for finding that. So 2.78 for our ionization energy, and it is in attajoules, so that's nice. Now let's write that. So ionization. Sorry, we need the ionization energy. I meant to look up lithium, my bad, 0.86, sorry. And then we need the electron affinity of fluorine, which I think we should have that on our notes. Do you have a page for electron affinities in the book? Somewhere in 7. Didn't we have a chart in our notes? There we go. So here's some electron affinities, except it's in kilojoules per mole. So if we want to use this chart, we have to do our conversion. So let's go ahead and do that since we do have these values. So again, I'll convert it to joules, so 328,000 joules divided by our Avogadro's number again, so 6.022 times 10 to the 23rd. And so that gives us 0.544 attajoules there.
Is it positive or negative?
Negative. I just didn't put it in the negative. So now we go back. So negative 0.54, I'll round it, 5. So this is all in attajoules. And so now we can add all these numbers up. So we have our Coulombic attraction, our electron affinity of fluorine, and our ionization energy of lithium. And so pull that from the chart, so I looked at the wrong one initially. And then, did anyone find the chapter 7 page to help people? I'll try to pull that up in the book. But then what do we get when we add these up? Let's hear some answers. Yep, 0.865. Excellent. Did other people get this as well? Good, 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 not good.
So this would be the energy.
Yeah, so this is the whole energy release then in this whole reaction, right? Because we added up our electron affinity process. So, right, fluorine's gaining the electron, lithium's giving up the electron with our ionization energy, and then, of course, the electrostatic forces. Yeah.
And a negative number is an energy release, you produce energy.
Yeah, and that's what.
Positive would be absorbing energy.
Right. Yeah.
Got it.
And so,
That was confusing.
yeah, but what you want is a negative number, right? So exothermic reactions are generally favorable because they're releasing energy, and then if you're releasing energy, that also is thermodynamically favorable, so things want to go to a lower state. And again, not that endothermic reactions don't happen, obviously, it's just that you have to put energy into them, so that would be not as favorable.
Is there a way to know how this energy would be released? Like, would it be in the form of light?
So it'd be like probably hot, so you might feel it when you're dissolving, if it's significant enough. So sometimes when you dissolve certain things, like especially sodium hydroxide, that gets really, really hot. And so, yeah, you might notice a little bit of warming. I mean, you could calculate it and then do it experimentally, but that's what is like those icy hot packs, right? It's different things, so depending on the dissolving process. So like some things, if they're endothermic, that could be used as like an ice pack where you crack it and then it actually takes energy to dissolve it. So then it's going to feel cold to you as the ice pack. And then other reactions, right, if it's an exothermic reaction, then that could be in like a hot pack. So that's all the difference there. Because usually all those hot packs are is like water and then whatever the substance is.
The units for this is attijoules times picometers, right?
So it's just attijoules because the picometers gets canceled out.
Okay.
Yeah.
I think what Misha was asking earlier was whether, like, I assume you saying that the energy would be released in the form of heat or absorbed in that form. What makes it heat that is the energy? Why doesn't it, like, flash a bunch of light when it dissolves? Like, how do you determine that? Yeah, how do you determine in what manner the energy will be released?
I guess it's like more with the mechanism, but because you have to think of like what's kind of going on mechanistically. So in this case, if you're having like electrons being exchanged, right, this is then what's going on versus like if you're doing light promotion, so something that like where you see light, you have to have electrons, like some sort of transition. So it just depends like what's happening and how reactive it is to, like burning magnesium, right? Like that causes it to go crazy and burn, and then of course you have the electrons being promoted with that process. But in this, if you're just dissolving, that tends to just be more of a either exothermic, endothermic process. But
In the textbook, if anyone gets confused, sometimes that energy that we just found, it's like E subscript RXN. They call it homology.
yeah, and so we could say this too. So E reaction, that's a good note. So it's just like your overall reaction, and then what you're seeing. Oh, and then I did find the electron affinity in the book. And so it did match actually what we calculated, which is always reassuring. And so it's on page 186 in chapter 6, and there's the electron affinities and attajoules. So I'll note that. So page 107 and 186 for some of these values. Or, of course, again, you can Google and ask the internet, but be prepared for slight discrepancies. All right, let's see how far we make it. Oh, I see the chat had the answer of 186. Let's talk about covalent bonding now. So covalent bonds, now we're talking about sharing electrons. And so electrons that are shared by atoms are called bonding pairs. And then we may also have electrons that are not shared, known as lone pairs or non-bonding pairs. And so let's take at least a first look at water for a second. And so we can start by drawing our Lewis dot structure. And so these structures, again, simple as they may be, can be pretty powerful. And so we have our Lewis dot structure. So 6 valence electrons filled up right appropriately with our s and p orbitals. And so now this also tells us, so we have these 2 awkward little lone electrons. So these are basically ready for bonding, is how I'd look at those. These are paired, so they're lone pairs. Again, not that they can't have interactions, but we need to start with making some bonds first. And then, of course, we have hydrogen, so let's draw its Lewis dot structure. We'll draw 2 of them since we need 2. Again, we have these electrons primed for bonding, so we can see hydrogen, right, wants to make 1 bond here. So it wants to fulfill that duet rule. And so now we can also see, okay, this is probably why they'd want to make a bond. And we can formally draw this little half arrow. So half arrows signify 1 electron movement. You don't normally really draw mechanisms for that. And so now I'll just redraw that with the appropriate colors just to kind of help. So we're accounting where the electrons are coming from. And so this is a normal covalent bond. And so normal just meaning that each atom is donating 1 electron. So this is not always the case, so sometimes you can have atoms donating 2 electrons. But that's a different type of bond, so we'll save that for another day. And then, of course, we don't normally write 2 little electrons like that. We want to change our shared electrons into, of course, 1 line. And so every line stands for 2 electrons. And so in this case, we have our single bonds here. And so now let's look at least our first look at the diatomics. So we'll later learn where our Lewis dot structure does not give us more information, so we'll have to save this for second quarter, unfortunately. But let's start with H2. And again, right, you can see probably why it wants to make a diatomic, 2 lone electrons. And so that would make sense that they would form a single covalent bond here, hence why it's H2 in its elemental form. And so now we can repeat that for our halogens. So if we just take fluorine, for instance, and probably should have filled that in more appropriately, but we still have the correct final answer. And again, we have 3 lone pairs now, and then this 1, so this is definitely ready for bonding. So we know the halogens tend to make at least 1 bond normally. They can do some funky stuff in covalent compounds, which we'll look at. But again, this explains why fluorine is a diatomic, right? And wants that octet fulfilled. And again, we have a single covalent bond. So now take a moment, draw what you think oxygen might look like as our diatomic. So just kind of play with it, count your total number of electrons, how many bonds you need. Then we'll look at it. And if you're in the chat, you can draw your answer, describe your answer.
You said what, 2 elements?
Oxygen, sorry. So try oxygen. Let me switch my color. And so what do we get for our structure? Right, always start with the Lewis dot structure if you need some inspiration. But how many bonds do you think will be between these two oxygens? 2, excellent. And so again, for doing these structures, we just want to make sure we have the correct total number of electrons, so total valence number. And so oxygen, 6 valence electrons, they each bring 6, so 12 total. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So hopefully your structure looked like this then. And looks like chat also got 2. So I think we're all on the same page. And then double check your structure. So this is important when drawing these Lewis dot structures is, does it make sense? Do we have a fulfilled octet? Are there other ways to draw this? And then we'll also analyze it with formal charges later. And so again, I'm just showing, so this oxygen on the left feels 8, so 1, 2, 3, 4, 5, 6, 7, 8, of course with those 2 bonds, so sharing those 4 electrons. And then on the right, same thing, so 1, 2, 3, 4, 5, 6, 7, 8, so they both are fulfilled by the octet rule. And so then try sketching out nitrogen. What would that look like? How does it differ? So what do we get for nitrogen? How many bonds between it? 3. And so right, each nitrogen has 5 valence electrons. So times 2 gives us 10 electrons. And so yes, you should have gotten 3. But then we also have a hint from our Lewis dot structure. So we look at this 3 lone electrons, so it probably wants to make 3 bonds. And so that looks good there. And so now this kind of goes back to Camilla's question on how do we predict the type of bond, what's the bond length, how do we describe it. And so part of this goes with our electronegativities, at least again it gives us a sense. And so these electronegativity values, so we mentioned, right, electron affinity and electron negativity are closely related, just with this minor discrepancy. And so let's kind of say what this is. So this is our electronegativity values. Oops. And again, we had defined it as basically, right, how much an atom pulls electrons towards it in a bond. And so again, we mentioned, right, that was the distinction between electronegativity and electron affinity, as electron affinity was just in the gas state of our metal. This is in a bond. And so it follows a trend. So the most electronegative is, of course, fluorine on the upper right over here. Most, I'll put E negative, so most electronegative. And so that leaves, right, francium as the least electronegative. And so what does this tell us? What can we do? And so again, this is just kind of a guideline. But what we have kind of defined is if we have a difference in electronegativity from 0 to 0.4, that's considered a purely covalent bond. And well, what does that mean? Well, if we have a pure nonpolar covalent bond, right, we have electrons equally shared. And so this could be in the case of like fluorine. So even though, right, fluorine itself is extremely electronegative, obviously the difference between them is 0. And so they would be sharing electrons evenly. And of course, how it's drawn here is appropriate. So we'll play some with computational software at least second quarter if I don't show you anything earlier. But computational software, again, will show you kind of where the electrons are based on how big these little balls are. And so again, even kind of ball shading, so they're shared equally. And so now as we continue on kind of the spectrum here, and again, it's all kind of a continuum. If you're doing research, right, part of what you're trying to discover is like, is this a weird bond? Is it too long? Is it too short normally? How does it follow the trends? And so those would all be things you would look at intimately. And so now what's kind of defined as polar covalent goes from 0.4 to 2.0. Again, you might see some weird oddities in research. You could always find some sort of discrepancy because it also depends on like what's going on, electron counting. So looking at all those details. So this is just a guide. But let's just see how you would do this. So now hydrochloric acid, that's a covalent compound. So our acid here, so Lewis dot structure. And so now we can calculate our difference. So we just subtract these values. So I would have to give you a chart on an exam or give you values, right? Or, tell you where to find it in the book or something. And then we just subtract, so 3.16 minus our 2.1. And so that gives us a difference in electronegativity values of 1.06. And so, okay, now we know that chlorine is going to be pulling those electrons towards it. And so you would see this reflected in your modeling software where you have a greater sphere here indicating greater electron density. And so you can see, right, the larger sphere. Now they include that partial negative sign. Again, just helping you to see that, yes, the electrons are located more on this side with the chlorine hanging out, and hydrogen has this partial positive since its electrons are, of course, being stripped from it, hanging out on chlorine. And then again, we continue with this continuum of bonding. And so around 2, that's where we say we have an ionic bond. Again, you could always find exceptions, I'm sure. And so if we practice it for sodium chloride, so chlorine again is 3.16 minus our sodium, so 0.93. And so this gives us a difference in electronegativity values of 2.23. And so that helps us see that it's ionic. All right, so let's just finish up. We're getting to the end here. So we do still have a quiz today just over like electron, what do we talk about? Quantum numbers, all that good stuff. So we'll just finish off here. And so like we were practicing with our structures, so we formally can define this as a single covalent bonds, again, 2 electrons and just 1 line. So there they drew out the 2 electrons, but we want to change that to a line. And then of course double covalent, just saying that we're sharing 4 electrons total with 2 bonds. And of course you want to draw our lines. And then it mentions elements that can double bond with themselves. And so this is not all inclusive, but definitely carbon, nitrogen, oxygen, sulfur, and phosphorus. They get into interesting bonding motifs. And then
Silicon. Just because carbon, nitrogen, and oxygen are right next to each other, and then silicon, phosphorus, and sulfur are all right next to each other below them. So does silicon not form double bonds with itself?
Not as readily as carbon, no. So that's part of why we're carbon-based life forms. And so basically carbon really likes to hybridize. And then silicon tends to either make these tetrahedral structures like silicon tetrachloride. It really likes oxygen too, so it likes to make silicon dioxide. But other times in chemistry, there is research interest in like the silanes, but yeah, silicon just doesn't tend to double bond like carbon does. Carbon is also unusually small. I can't spell unusually small. And so that also probably leads to its tendency to hybridize and then do a bunch of crazy bonding. But yeah, that's something that research scientists have been trying to do is, for example, like benzene. So this structure. Sorry, I'm drawing it explicitly, so it's taking me a long time. So benzene exists obviously with carbon, but at least last time I checked, they have not made this structure with silicon. So that's something that they're trying to do, but yeah, silicon just does not behave the same way. But yeah, you would have to dive more into it as well to continue explaining. And then triple covalent bond. So again, like we saw, I don't like how they drew it like this, but whatever. So you want to draw it with our lines between them. So again, 6 electrons being shared. And so those will be the types of bonds you see. And then you can have carbon-nitrogen triple bonds. And usually don't really see oxygen triple bonds, but you could see oxygen and weird bonding motifs, which we'll look at. All right, that's a good point to stop at. And so we'll take our 10-minute break, and we'll do our quiz. And then that'll be that, and then you can hound me for your exam grades. And then I'll hang around on stream for another minute or so.
Oh, I'm happy with that. That's very nice. Very nice. Fix that.
It'll be over the stuff we did, like the quantum numbers and like Schrodinger stuff, like just the basic stuff about that. How many electrons are in different energy levels, orbital stuff.
So just a question about the chapter 7 homework. When I asked for the bond polarity, I was a little confused because I saw in your homework answers it's just a yes or no.
Oh.
Is it yes or no depending on this chart, or because I was writing down the specific like bond type there.
Yeah.
I was just a little confused on the bond polarity part.
Yeah, because you might want to say two different things with this. Because with the bond polarity, you want to recognize there's two things. Like, is the bond itself polar, but then is the overall molecule polar?
So
like,
it's yes for.
Yeah, so
water.
it's yes and yes for that one,
Yeah.
and then.
I guess just my question is how you would find out something like for this, like for CH2F2. How would you
Yeah.
find it?
So then that one, right, if we look at our electronegativity chart,
Yeah.
so the CF is probably going to be, or not,
The difference between.
carbon fluorine, sorry.
Yeah.
The carbon fluorine bond itself is going to be polar, right? But then, of course, the carbon hydrogen, that's going to be less polar.
Okay.
So then what that's going to do is, so your carbon fluorine bonds will be polar, but then you'll have unevenness in your molecule then, because you'll have half of it be polar, the other half is non-polar, so
Right.
then that makes the whole thing polar.
Okay. So you would just subtract the electronegativities like we do and then look at this table.
Yeah.
And if it falls in this range for the difference, then it's polar.
Yeah, then you're saying that bond is polar. Exactly.
Okay. Thank you.
Yeah, and then the next step is figuring out, does that, because, right, do you take physics?
Yeah, I'm taking
Okay,
physics right
perfect.
now. Yeah.
So then, right, then you're adding up all the vectors and seeing,
Okay.
is the charge canceled out, so you have no
Right,
overall polarity,
right.
or
I saw
is there?
a little bit of that in the textbook that talks about. the
Yeah,
vectors
so if
and
you
just-
understand vectors, that's easy
Okay.
for
so,
me.
Right. So
then you're
there's-
just adding the vectors of which direction they're going and whether you have
Okay.
movement or not.
Gotcha. Thank you.
I didn't hear you. Did you say that our tests were graded?
They are almost graded, so I have to grade like the back page. But yeah.
Sounds good. Thank
Oh, and I'll do another surprise for you guys. So instead of this quiz being like a quiz, today's quiz will be bonus points on your midterm. Yeah, you definitely need them. So that'll hopefully help slightly lift your grade a little and you won't stress as much, maybe.
Actually, I had a question about the correcting of our exams. So do we get to correct like up to 70%, like total, or do we?
No, you'll get 70% back for each problem. So, if you got like a 90% and then you only missed 10 points, you could correct those 10 points to get 7 points back.
Okay.
So if it's ground, it would just fill up normally like this one, right? You just start off 1S1. Well, that's not anything crazy. 1S2. Well, that's still just following your normal
Yeah.
thing. But then this one, 2S1, we don't start at 2S1 normally, right?
Yeah,
You
no.
normally. So then, okay, well, that has to be excited. And then you look at this one, 1S1, 2S.
2S2. Usually 2S2.
Well, and you can't start with 2S1. You have to start with the 1S normally.
Oh, yeah.
And then this one, right, before we go on to the 2S, we should have filled up that 1S2, but since they didn't, it's excited. Yeah, and then that one, I think, fills normally. But then this one's excited.
Instead of doing like a dot dot or whatever.
So if we look at, so let's pull up a periodic table. So then this one is argon, and then it says 4s2, but then it goes 4p1, right? So we skipped all those D's, so this one's also excited. Versus the neon one is fine, right? Because neon 3s2, 3p1, so that's not excited, so that's ground, but that's excited.
Okay.
Yeah, so just see if it fills in normally or not, and then if it does jump or do something weird, you know it's excited.
Okay. Thank you.
All right, I'll go ahead and hand out the quiz. Yeah, because, oh, you're fine. Uh, let me, let me find yours and then I'll. Okay. Thank you. Huh? If I find yours, I'll put you on the list. Yeah, I can, oh, it's only 12:08. Oh, I actually found yours. Andrew, I'll try to find yours after. I just found Tori's first. No, I just need it back.
Yeah.
Oh, on the laptop. Yeah, thank you. Oh, yeah, Katie hasn't been here this week. Where's she at? You know, your exam's the last one.
Of course,
Trying to find it.
must not be out the test.
No, I haven't. This is super raw, so I was blind grade. Thank you. Sweet. Oh, where's your exam?
Yeah.
Okay, I didn't find it.
We wanna, I can't blanket, blanked how to do that controversial. For the finding when temperatures equal each other.
Oh, yeah. Hang on, I didn't find yours.
Okay.
Just now I have to look. Are you wanting your exam? Camilla?
No, I just have a weird question about chemistry.
Oh, yeah, go.
So if you were to put like a small amount of like a pure substance, like for instance, I guess you do like carbon or something, and then you put it in like a really strong electrical field, of like just like that's all negative. Could you push the electrons closer to the nucleus? Or like, is there any way that you can push like the outer electrons closer to the nucleus? Like, can you like squish an atom?
It's an interesting question.
Yeah. And then if you can't, will the electrons just like stick to the protons? And then like, because like I'm always confused on
All I
how.
kind of think of is like how they do how they use the huge superconducting magnets to like confine plasma, which is kind of, I don't know if it like works at the atomic level, but it kind of confines the electrons and those atoms to a certain spot with the magnets.
That's true.
Yeah.
That's all I think.
So like, I think it would be pretty cool
Yeah,
to
it's
like
interesting.
attach electrons to the nucleus, because like if you get the electrons close enough to the protons, they should just stick together, right?
Question.
Well,
Because I think the protons themselves are what's holding the electrons together.
Right.
okay, what's your question?
The final exam, I'm assuming it's on the last Thursday of the term.
Yeah.
Could there be a possibility that I could take it on Monday during your?
Yeah, you
Okay,
could do that.
okay.
Just, can you shoot me an email just
Yeah,
so it's
yep, I was
on my
planning on it. Okay.
radar?
I've got one for you.
Thank you. All right, here's yours. No, I just need it back because I don't have grades recorded.
Here you go.
quiz, yeah. Thank you.
Could I see mine?
Eugene? I am literally tallying yours up.
Oh, right now.
Do you have a tally though? And then, yeah, I just need it back.
So would I get extra credit or just?
Oh, yeah.
Okay.
Yeah. Yeah, everybody gets a fair amount,
Thank you.
yeah. And then, and you could also have exam corrections, so that's also available to you as well.
What'd you say?
I said if you also wanted to, there's also exam corrections.
Awesome,
So yeah,
okay.
you still get, everyone gets advantage of it.
Yeah, there's unit conversions, I swear.
Yeah, pretty
Yeah,
good.
thank you.
Thank you.
And I was wondering about the exam corrections. Would that be something we'll be doing right here right now, or?
There'll be like a take-home thing once I get them
Oh.
back to you.
Mhm.
But yeah.
Okay, cool. Yeah, I think I got the same one that Andrew got around with that, finding the point where they both have.
Yeah, a lot of people had algebra issues.
I can't believe I forgot the system of equations because it's so easy. Like we went and did it afterwards, and it's like the easiest thing. We just both.
That
think a lot of
always
people do.
happens on an exam.
But yeah.
Did
And
you
then-
want to see yours, or are you creeping?
It would be nice to. There was one that I think I got quite wrong about the subatomic particles because Dusty was like, "Oh, he really pointed it out." He said, "Oh, something about the which of these particles subatomic cannot be more than one and all that." And I changed my answer like 4 times
Oh,
because
no.
I wasn't sure, and I went and looked it up, and I was like, "Oh, I did the wrong one."
Okay, let me. Oh, actually, I just graded yours, so that's convenient.
Hopefully, it's not.
And then I think I did grade yours. Cause you're in Madden, right?
Mm-hmm.
Where I can utilize exam. Oh, thank you. Thank you. Oh, yeah, you can.
And should I give it back, or would this be more?
Oh, yeah, I just haven't recorded the grades, but once I record them, I'll hand them back to you, and then you can do corrections. Yeah. So confused.
I didn't even know it.
When you come to mine, can you call me?
Yeah.
I have to see how it's doing.
Yeah, I can fish yours out too. Thank you. Thank you. Thank you.
So I was wondering about my exam, like getting it done, like if you could get it, like when will I know information on it? 'Cause
Let me see if I can find yours. If you stick around, I'll do it right now.
Okay.
It-
You might wait, because, just so
Yeah.
I know.
It doesn't take me too long to, because I have everything graded but the back page and the adding.
Okay.
So just give me a second.
Went away.
You want me to fill in?
Thank you.
phone. Like, I know, that's why I told you to ask him. And then like, eventually got so fed up, I was just I was like, so, when are you gonna call me about something
Are you creeping?
Yeah.
Okay, I will search for yours once I tell you.
No, I figured the last couple times, 50 times you called me was to, yes, you asked me for a ride. When I clearly have better.
Okay, Sabrina.
Thank you. Do you need it back, or am I good?
Yeah. Do you have lab today?
No, I did on.
Oh, okay.
Right now.
Yeah, unless you're trying to like get a head start on corrections. I still have the grade recorded. Okay, let's see if I can fish out yours. Thank you.
I'm gonna take a picture of it so I can see it.
Those are extra.
Oh, that's fine. Thanks. And then Audrey, I'm just adding right now, and then I'll have yours. Audrey. Yeah, I'll just need it back since.
And for corrections, what will you need to do?
What I'll do is once I hand them back, unless, like I said, if you really want it now, I can record your grade and give it to you. If you want some time with this. But yeah, you would just like do any of the ones that you did wrong.
Okay.
You can, show your work.
Okay.
And so like literally any place, redo it, get some points back.
Okay.
And then I'll regrade it, right, take the total number of points earned and then multiply that times 0.7 and that'll be added to that score.
Okay.
So did you want
I
to?
think so, yeah.
Okay.
Because I'd like to get that.
Let me just record yours then. And if I haven't even made. Give me a second. Where's our midterm category? Yeah, there's just so many of you. I didn't quite make it through last night. I was trying. And then. Oh, yeah, you can put it here. Sorry. All right. There you go. You can have that now.
Thank you.
Is
the sum of this just you add up each of the sections? Yep. And
Mhm.
then that's out of 100?
Yep.
Thank
Yeah,
you.
you did nicely. Oh, you can stick it here.
And then you have the copper rations as this week's one.
Yep.
I was wondering, were you telling her that you're gonna allow us to like fix not
Yeah, so I'm doing exam corrections for everybody. So if you're dying to see it and dying to correct it, I can give it to you now. Did you?
Yeah.
Yeah, let me, so.
If it's good.
Oh, I'm super close. I just have to add up the last page. Just trying to find yours. This was graded, but I don't remember seeing your name graded. Here's. Did I grade yours? Yep, I did grade yours. And then I can record the grade if you want it.
Are these finals?
So those are the page totals, and then the final is that grade. And then you can always check for addition errors or anything. But yeah, you can take yours home. I stuck your grade in the grade book. Slowly catching it. So now you people here can take your exams.
What was the grade that you made for pass?
So I don't know what the passing grade is, because I don't have any exams statistics yet, so. But in general, I'm not trying to fail people, but I think you're more of the like middle higher pack. So like I said, I don't have an average, but
Okay, so this is like you say with okay.
yeah, like I'm not concerned about you.
Okay. And you said I could take them.
Yep, yep.
Thank you. Have a good day.
You too. Yeah, just keep it up, and then the exam corrections will help you. Bonus points will help. So I'm hoping all the grade inflations will mean that I won't have to like do any normalization at the end. So that's what I do at the end is, I take everybody's grades, and there might be some normalization, usually in your favor.
And then for the like corrections, can we do those at home or do we?
Yeah, so you can take it home and then bring back, your sheet with all the corrections.
Thank you so much.
Yeah, no problem. And I have your midterm, and you can also take yours home. Yep. put pressure on you.
Everybody he was doing so far last time that I was so scared.
I think like I said, I haven't done any data analysis. I think I have a bimodal distribution, if I had to guess, for people either like did pretty good or they kaputted. And some along the middle. Madeline, did you want your exam or? You're like the last victim here, and I have yours graded.
I want to correct it desperately, but no, because I'm afraid of what I'll see. Thank you.
I'd say you're probably in the middle-ish pack, but like I said, I don't have exam statistics.
That's right. That's already. I'm so scared. And of course, if there are grading errors, let me know.